Okay, so the last topic, moment of inertia. So learning objective today is calculate the second moment of inertia and determining this by direct integration and determine moment of inertia of composite shape using the parallel axis theorem. Okay, very important for either final exam takers in project. Yep. Okay, so second moment of inertia. Let's start this definition from first moment of the area. So we already learned first moment of area when we calculate the centroid, right, earlier in this semester. What was first moment of area? Moment was force times moment arm, right? And then moment of area is area times moment arm. What is moment arm? Distance from the reference axis to the centroid, right? So we defined moment of area about x-axis as area times y bar, right? Area times distance from the reference axis, x, to the centroid, right? So qx is y bar a, qy is x bar a, right? Do you remember, right? And then second moment of inertia is very similar concept. So it's moment of inertia. So inertia is quadratic and then second order term. So instead of this y bar, we are using y square in the integral. Okay, so that's mathematical definition. Okay, any questions? Okay, good. And now, how to calculate the moment of inertia of smooth shape using integration, right? So this is the equation I show you, and then smooth shape, something like this, are defined, and we want to find Ix and Iy, right? And then it's infinitesimal procedure, so we'll cut many sections and then integrate, right? So that is the idea. And then how to cut? For Ix, we cut parallel to x-axis. So Ix cut horizontally, Iy cut vertically. Okay, and then define dA. dA is area of this small strip, right? And then use these two equations to find the moment of inertia. Okay, then I think the first problem is about this one. So let's solve this problem together later. And then another important concept is radius of gyration. So the motivation to define this radius gyration is this. So first moment of area is area times moment arm, right? Y bar or x bar a for qi, right? And then is there anything similar? Right, any similar equation for moment of inertia as well? So that is motivation to define radius of gyration. And then if we express something like this, so Ix is something square times a, so this times a, or this square times a, so that's the difference between moment of area and the moment of inertia, right? Then these terms in the empty space is radius of gyration. So for Ix is Rx, radius gyration in terms of x-axis, and therefore Iy is Ry, right? So radius of gyration is kind of derived quantities from moment of inertia and the area. So how can we find this Rx? So if we equate this to, so can I use this? No. Equate this to Ix and then Rx squared and x. What should be Rx equation? Rx squared should be Ix divided by A, right? And then now our square root of both and side, then Rx should be square root of Ix over A. Something like this. And then Ry is square root of Iy divided by A, right? So any question about this concept or derivation? No? Okay, good. So, yep, transition to the second learning objective, so moment of inertia of a composite shape. Yep. So, for the simpler shape, all the equation for moment of inertia are defined here. And then for composite, okay. Yep. Okay, then for the composite shape, we should use divide and conquer method, right? And then before talking about the composite shape, I brought this quiz. So the section of higher moment of inertia can resist the higher bending moment. That is the motivation we are learning moment of inertia today, right? So higher moment of inertia means higher bending moment capacity of the cross section. Okay, so then this is the same cross section. It's rectangular beam, 10 by 30, and then 10 by 30. And then so there are two cases, and which arrangement can resist higher bending moment? So this is the moment of inertia equation for a rectangular shape. And what do you think? So I will activate the clicker here. Yep, as usual, feel free to discuss with your peers and then choose one option, either A or B. Okay, I'll close after 10 seconds. Okay. A has more votes than B, right? And it's right. So A has higher moment of inertia Y because of this equation, right? This is B. B is 10, H is 30, then 30 cube, right? That is greater than 1 over 12 times 30 times 10 cube, right? So based on mathematical calculation, we can see this one has higher moment of inertia, and because of that, this kind of section can resist higher bending moments, right? So what does it mean? So I like to show you some demonstration here. So this is kind of extreme case, right? So it's my notes, right? And then this is cross section. Maybe this is 1 millimeter here, and then maybe 8.5 inches letter size, right? Right. And then if we use this cross section for the bridge, right? And then what is bridge? It's a horizontal shape, and then there is a load here, right? And then what is bending moment? Bending moment like this. Something bending this beam, right? And you can compare these two cases. First one is this configuration, and then loads are here, okay? Here, right? And then try to bend my folder, but it is very hard to fold, right? Higher moment of inertia, higher resistance to bending moment. And then the second case is this, right? Using this cross section, and then beam, right? And there's a load here, and then moment, much easier, right? So either this, right? This or this, right? So even though we are using the same cross section based on the arrangement, vertical or horizontal, it matters, and then its effect is different. So I like to show you this from this clicker quiz, and I hope that helps. Okay, and then let's move on to the second one, so this is kind of discussion, it's a conceptual understanding of this one. Which arrangement is more economical, cost saving, cheaper to carry the same amount of bending load, bending moments? What do you think, A or B? Economical? Yay, right, A is economical because with same cross section, A can carry much more bending moment, right? So if we need to carry the same bending moment, we can reduce the cross section. So that is economical, right? Okay, and then this is real world example. So we need this deck to carry the passengers and vehicles, but these beams are load carrying members. Okay, load carrying member looks like this, and then majority of the sections are vertical shape, and then we use wide beam that has very high moment of inertia. Now, this is the last topic, parallel axis theorem for a composite shape. So, moment of inertia of composite section. Typically, we are all engineers, and then we are dealing with composite shape like this, and then these are some of the wide section here, right? And then, as I mentioned before, we'll use divide and conquer method, right? So we'll divide the composite shape into simpler shapes, right? And then find the centroid. That is very important because of the parallel axis theorem. And then that's this one. So parallel axis theorem is this: I, moment of inertia of the section, equals to moment of inertia about the centroidal axis. So each shape is centroid, right? I0 is moment of inertia about the centroidal axis. And then plus A area times D square. And then what is this D? Distance between the centroid and the reference axis you are calculating moment inertia with. So this I can use different axis than centroidal axis. If we use this one to calculate the centroidal axis, then these two must be the same, right? And then if they are different, then we need to add A times D squared. Okay, so I'll show you one by one, so I repeat. A sub 0 is moment of inertia with about centroidal axis. And then you can use moment of inertia table I showed before. And then A is area. And then D is distance between the axis of calculating moment inertia with and the centroid of each section. Okay, and then this is very important, and we'll practice in the second problem too. But this is very important. And then here we are calculating moment of inertia of the composite shape, and then we divide each simple shape, right? For simple shape, we calculate the centroid of each shape, right? And then calculate the moment of inertia of each shape using the parallel axis theorem, and then add moment of inertia this time for all subsections. So we are adding sigma sign here. Okay, so divide and conquer, and then for subsection, we find the centroid, moment of inertia, and then sum them up. And then when you sum them up, you need to consider the signs too. So if it is cut out, you need to subtract, right? And if it is added, then you can just add up, right? So this page is very important, okay? And then I think this is the last clicker quiz. So we want to calculate the moment of inertia of this shape, subsection, about x-axis. Which one is correct equation? Using the parallel axis theorem. So this is the parallel axis theorem, and then I0 equation is here. And then as you notice, this is the same, area is the same, and then the question is, what is D? What is D, right? dx, what is dx? Okay, I close after 10 seconds. So we have C, the most food, and next B, and D and A. Okay, okay. So today I don't think I can use this. So can I use this mouse? Okay. Okay. So what is the distance between the centroid and the axis of calculation? What is the axis of calculation? X, right? X-axis. So x-axis is here, right? And then what is the centroid of this shape? Center, right? Center, right? Then what is the distance between this and x-axis here? So it's not 6. 6 is the height of this shape, right? And then 24 is distance between x-axis and the lower, right? And then 30 is distance between x-axis to the top surface, right? So that's why C is correct, right? So that's what dx is. The first page is this one. So first problem is 9.4. And sorry about very small font, but this is y equals k times x cubed. And this is A, this is B. Okay, and then as you expected, this is direct integration to find moment of inertia of the shaded areas under this curve with respect to the y-axis. And as usual, let's find moment of inertia in both axes, x and y. Okay, so now we don't like this k, right? So we like to express this k in terms of a and b, right? What can we do? So use this coordinate a comma b to this equation. So y is b and x is a. Then we figured k is b over a cubed. Then the equation becomes to y equals b over a cubed, x cubed, right? So this is kind of pre-processing before solving any direct integration problem, if you see k. Okay, any questions? Okay, now start with IY. So what is IY equation? IY is integral x squared dA. So I'll give you this equation, but I recommend memorizing this one or know this one. So IY, x squared dA, right? A times something square, and then that should be the opposite one. And then it's integral, so we need to cut section, right? So for IY, which direction should we cut? Horizontal or vertical? Vertical, right? Parallel to the axis. So let me use this one and then cut like this. And then dA is area of this strip. And because we cut in vertical direction, B, base, should be dx. And then height should be y. Right? And then dA, so area under this rectangle should be y times dx. Okay, so now we found the A, so let's use this equation to find IY. So integral x squared times dA y dx And then we know what y is, right? B over a cubed times x cubed. So x squared and then b over a cubed x cubed dx. Right. Now a and b are constant, and then we have 2 x's, 3 x's, so x to the fifth, right? So b over a cubed x to the fifth dx. Now we can integrate, and then what is the integral interval? Between 0 to a. Right? So I think this is easiest integration. So b over a cube, and then x to the fifth, so 1 over 6, x to 6, from 0 to a, so answer should be 1 over 6, a to the 6, and then a to the 3, so 3a is gone, so a cubed b. Right. So any questions? So I started with y-axis because calculation is easier. And then now x-axis. So x-axis, we just switch this one as y, right? So it's integral y squared dA, right? And I'll plot this curve again, right? So this is A, this is B, right? And then for IX, we cut horizontally, right? Here. And then because we cut horizontally, the height is now dy. It's small, thin strip. Yeah. And then to calculate dA, we need to know this base, right? What is this base? This is A, and then this is x. So this should be a minus x, right? So a minus x is base, and then dy is the height. So this is area of this strip, right? Okay, and then now we found dA here about in terms of y, and then y squared. So I write it again. You can use this space and to write it here. So y squared a minus x dy. So this is what we have so far. We have y here, x here, but we want to integrate in terms of y. Can we calculate it? No. We need to express x in terms of y, right? And going back to this equation, it's, easy case. So if we multiply a cube and divide by b, both ends side, we have this equation, right? And then, triple root, right? So then something like this. Then what happens? X equals to a over b to the 1/3 times y to the 1/3. So instead of this, I recommend using this indication because it's easier to integrate. And then once we do this, we can substitute x to this place to make everything in terms of y. So y squared times a minus x, x was a over b to the 1/3 times y to the 1/3, and then dy. Okay, and then it is integration in terms of y-axis, so integral interval should be from 0 to b. and then conduct the integration. Right? So yep, oops. Something wrong. Yep, so it should be like this, right? Yep. Yeah. Okay. Then first term is a times y squared, and second term is a over b to the 1/3, and then y squared, and then y to the 1/3, 2 plus 1/3, right? So 7 over 3, right? So y to the 7 over 3 dy. Okay, and then I'm sure you can integrate the first one. So that's a times 1/3 y squared, y cubed. And then the second term, what happens? So what is the integration of y to the 7 over 3? 3 over 10 times y to the 10 over 3. Yes, thank you. Okay, so, and it's from 0 to b. So the first term, 1 over 3ab cubed, right? And then second term, 3 over 10. And then we have b to the 10 over 3, and then 1/3, right? So 1/3 is gone, and then we have b cubed. So this is a b cubed as well. Okay, so this cake is 1 over 3 minus 3 over 10. 1 over 30, ab cubed. Right? Okay, any questions? Okay, so here, if you want to develop a problem for final project for direct integration, think about any new equation, quadratic function or cubic function, and then try to cut section parallel to each axis and integration, right? Yep. So it's IY and then IX. Any questions? Okay, then move on to the second problem. Okay, sorry about blurriness as well. So the shape is this upside down T shape, and this is 6, this is 2, and these are 3 inches. So everything is in inches. Okay, so this 3, 3, 3, and then 6 and 2, and determine the moment of inertia Ix bar and Iy bar of the area shown in the with respect to centroidal axis respectively, parallel and perpendicular to side AB. So side AB is this one, and we need to find the centroidal axis. So what is the centroidal axis? X going through the centroid, right? Y through the centroid, right? If there is a centroid somewhere between here, right? And then X, centroid the x-axis, centroid the y-axis, and then moment of inertia based on these axes, right? And is this centroid the axis given? No, that means we need to find it. So that's why I determined the centroid. And then define the center of the axis first, and then calculate the moment of inertia about those two center of the axis, and then calculate the radii of gyration. Yep. So it's a 3-part problem. Very possible to be in the final exam, right? So let's try to find the centroid. Okay, 1. This composite shape, we'll use divide and conquer. So divide. 2 rectangles, right? 2 rectangles. And let's use first one as 1, second as 2, right? And you know the centroid equation is something like this, sigma x bar A over sigma A, right? So we can easily calculate the area and the x bar of each shape. So to find x bar, we need to define the baseline. And maybe easiest one is using the bottom here line here as x-axis. And then the far left axis as y-axis. But these 2 lines are not the central axis. It's assumed baseline, okay? Then you can choose any assumed baseline, but using that you can accurately calculate the centroidal axis from whichever axis you define, okay? Okay, so it's a simple shape, so you can use this equation as is in the exam or homework, right? So you can find x bar. So what is x bar? X bar is the x coordinate of the centroid of each shape. So where is centroid? Here and here, right? And then what is area? Area is something like that, right? So you can calculate. But if you are given a little bit complex shape in the exam, then I still recommend using the table method, okay? So table method, first line header, and then 2 lines for each shape, and the last line for the summation. Okay, and then the first line plus minus, right? And then second one, section. We have 2 sections, 1 and 2, and both ones summing up together, so all plus. And then now easiest one first, area of each shape. This area of the first rectangle, 6 times 3, 18. Area of the second shape, 2 times 9, 18. Right, so area is 36, right? And then what about x bar? X bar is using this baseline, x coordinate of each centroid, the centroid of each shape, right? So x bar of the first one, 4.5 from here to here, right? So 4.5. What about x bar? X bar for the second one? Same, right? 4.5. Great. And y bar. Y coordinate of each shape. For the first one, y bar 1 is this one, right? So 2 plus 3, so it's 5. And then y bar for the second one, 1. Great. So, and then once this is done, you can just use calculator to find x bar times a, y bar times a, and then divide. So for that, that's what we already did. So I'll give you the numbers. So you don't have to write down. You will have my notes. So x bar a, what is it? 81 and 81. Y bar a, it's 90 and 18. And then plus plus, so we'll sum these two, 162, this two, 108, right? And then using this equation, so sum of x bar a is 162, and then area, total area is 36. So this one is 4.5 inches. And then y bar, this sum of y bar a, 108. Entire area, 36. So the result is 3. Okay, any questions? So this is kind of review, but we found the centroid of each at this composite shape, and that is 4.5, comma 3. So from here 3. So this is the centroid, and then centroidal axis I'm using blue, and then indicate as x prime. So this is centroidal x-axis. And then this is centroidal y-axis. Okay, and now we need to find the moment of inertia, right? So to moment of inertia, so this is composite shape. It's not direct integration. We'll use parallel axis theorem. So parallel axis theorem means I equals I0 plus AD squared. And if this is about x-axis, then this is I sub x, and this is I0 sub x, and the area is the same. And then this is D sub x. Okay, and then we'll find it. So for moment of inertia, also table method works the best. So let's use this 4-line table. Right? And then I also use plus minus column for the moment of inertia as well. And then this one is easy, all positive. And section 1 and 2. Okay, and then now let's choose x-axis first. So moment of inertia about x-axis. So x prime axis, right? We need to find about centroidal axis. So moment of inertia about x prime. So where's x prime? So I use this one. Okay, so this is x prime, right? Okay, and then first one, we need to find I0 about x prime. I0 is moment of inertia equation, right? And for rectangle, we already know the equation, 1 over 12 BH cubed, right? So for the first section, 1 over 12, what is base of the first one? 3, and then height, 6, right? So the first one, 1 over 12, base 3, height 6 cube, right? So that is I0. And then the second one, 1 over 12, and then now what is base? 9, yes. And then what is it? Height? 2, right? 2 cube, right? Okay, so for this, I give you the number. So this is 54 and this is 6. And we already calculated area, so area is 18. Good. And now, what is the distance from x prime axis? So I'll show you this again. Okay. And from, I told you the centroid is here, right? And then x prime is here. What is distance between x prime to the centroid of 1? This distance. There is 3. Any other? It's very close. 3 is half, right? So this is 6. And then 3 is distance between this to this. And then what we are calculating is distance between this to this. 2. Yeah. 2 is correct because what was the centroid? Where was the centroid? Here. Yeah, 4.5 comma 3, right? This is 4 point comma, all right, and then 3. So this distance is 3, right? And that means the half of 6 is here. So this is 3, and then this one is 3 minus 2. So this small distance is 1. 1 and 2, right? So dx1, dx prime 1 is 2. And then what about 2? So distance between x prime to the centroid of the second section. I told you this is 1. And then what is this? 2 again, right? So this is 1, and this is half of 2, so it's 1, right? So this is 2, okay? Right. So then the equation is here. So we can add these two up, right? So we said this is 60, and then what about a times dx prime square? So 18 times 2 square, so that is 72. 72, same thing, 72. And then when we sum this up because of this, 144. And now ix prime is sum of these two plus sum of these two, 60 plus 144. So it's 204. Any questions about ix prime? Okay, then move on to iy prime. So first thing, calculate I0 about y prime, right? So to show you this one, so we are rotating this axis 90 degrees, so x to y, right? X prime to y. So the equation, the moment of inertia equation is just switching b and h. So instead of 1 over 12 bh cubed, so if this is I0x, I0y should be 1 over 12 hb cubed, right? So we are switching these two. Okay. Then, what is first I0? 1 over 12 h6 b 3 cubed, right? So I just switch this two, right? And then the second one, 1 over 12 h2 b 3, 9 cubed, right? Any questions? But it's just new, right? So for y-axis, it's 90 degrees, so it's b and h are switch it. Okay, then the calculation, so I'll give you the number as well. So 13.5, and then this 121.5. And a is the same, and now dy prime. What is distance between y prime and the centroid of each shape? 0. Great. So I'll show you this figure again. Y prime is this axis, and then both centroids are on this y prime. So that's why dy prime is 0. They are on the axis, no distance. Okay. Okay, and dy prime is 0, so the second term is gone. So we can just sum these two up, right? So it's 135. So iy prime is 135 inch to the fourth. Any questions? So we calculated moment of inertia about the centroidal x-axis and the centroidal y-axis, and which one is higher? X prime. So x prime is called strong axis. And then y prime or y-axis is called weak axis. For the rectangular shape, it doesn't change much, but it will change. Yeah, if it is thinner, then it will change much. But for the y section or some channel section, IY, IX are totally different. So there are so much difference in strong and weak axis. And the last one is finding radii of gyration. Okay. So radii of gyration are sub x square root Ix over A, right? So it's kind of derived quantity from moment of inertia, right? And now we have everything. So square root of 204 divided by 36, right? And then Ry prime, same with different index, right? And we found this 135, and then area is 36, right? So when you calculate this, it's 2.38 inches and then 1.94 inches. Okay, so this is strong and then this is strong. So x prime x is strong, so we must use strong axis. So that is the lesson, okay?